All right, so now we are going to start to talk about dislocation reactions. So it's really critical to determine, again, we looked at forces and stresses on dislocations, dislocation motion and velocity, but we need to see which reactions are going to be spontaneous and which reactions are not going to be spontaneous. And one way to see if a reaction is going to be spontaneous is by using Frank's rule. So the Frank rule basically states that the energy per unit length is proportional to the square of the Burgers vector. So the sum of the squares of the Burgers vector must be less than that of the products in order to be spontaneous. And so we've already thought about that for one, where two edge dislocations equal and opposite react, and that will be basically 2b squared versus 0. That is a spontaneous reaction. But one of the questions is, how do we generate new dislocations? So we could generate dislocations from dislocation sources, heterogeneously or homogeneously nucleate dislocations. So one of the main ways that we can develop new dislocations is from dislocation sources, specifically Frank-Reed sources. So the idea here is that you have some dislocation segment, and it's pinned at two ends. And when you apply a shear stress, that segment will tend to bow out. And it'll bow out until it reaches a maximum curvature, at which point it will then start to fold and then curve in on itself and then nucleate another segment as it pinches off. So there's some curvature associated with this bending. Initially it's 0. It's maximized when that R reaches L over 2. And we can look at the stress required in order to do this. And we can find, again, some critical shear stress required, and that should be 2 capital PI. That is our critical stress beyond which the curvature will actually be reduced. So again, it's attached to the pinning points, and then once they eventually touch, then they start to initiate, and basically the segments can, equal out, they can annihilate, and they will create essentially new dislocations. You could also have other dislocation sources too. So you can see again that bowing out and then leaving behind that dislocation piece. You could have other Bardeen-Herring sources as well. You could have heterogeneous nucleation from defects and other types. So here you can see kind of this out of plane, similar type of nucleation mechanism. So you could have heterogeneous nucleation. You could also have dislocations homogeneously nucleated from basically within part of a single crystal. But one of the key things that we're looking at specifically for the mechanical consequences of these defects is the formation of sessile or non-mobile defects. So that will actually dominate a lot of the plastic deformation behavior here. So let's look at one example of a Lomer type dislocation that may be sessile. So we can first check to make sure is Frank's rule basically satisfied. And when we do that, you can look at a squared versus a squared over 2. So it is spontaneous. Excellent. But now we need to figure out something very important, very critical. We see the, basically our resultant Burgers vector, but what's the plane? What is the guide plane of this new dislocation? How can we calculate that? So we actually have to go back a step, calculate where our tangent vector and the normals are in order to solve this problem. So we know that the first dislocation or initial reactants are in 1, 1, 1 and minus 1, 1, 1. So we can use this now to calculate the normals. So as we kind of just said before, we can actually write, again, there's the 1, 1, 1 plane in our minus 1, 1 plane here. So those are our planes. We also know that, so actually we could type those in. So let's type in our T edge, or actually not our T edge, our T result will be equal to across. So that will be our new, again, tangent line there, divided by the norm. Actually, that's not really our T result. It's going to be basically that's our tangent vector. That results from that. Excellent. So that's the tangent vector. That's the line of intersection, effectively. So if I cross the normals of two planes, I can find my line of intersection. We already have our Burgers vector, as we see here. So now I can find my normal to the plane, my glide plane, effectively. So again, I have two normals to two planes. The intersection of that will be my tangent vector. So I need to cross those two normals. I have my Burgers vector that results from the reaction, and then I can then solve for my normal to my glide plane, which will be my guide plane. So we see this is an FCC material. So that plane was -1, 0, 0. That's not a close packed plane, and even though we're along the close packed direction, that is not going to be a basically a slip system that we are going to work with. So again, you can see, remember, normal, to find that line of intersection, the tangent vector, I need to take the cross of both the normals to the plane, solve for my tangent vector. The Burgers vector is given from that dislocation, and then finally I could find that glide plane, which in this case is that -1, 0, 0, as you can see here. Again, that square root of 2 you can divide out, and again, we can basically try to normalize that. But this is the key aspect that we find here. So this is not a mobile dislocation by any sense for FCC. Even in simple cubic, it would not be so, because it's not close packed direction. So it is not a close packed plane, this 1, 0, 0. Even though we're in a close packed direction, it's really not going to cut it. So that was good, but again, it's still not going to work. So this is a critical way to kind of see, and again, these sessile dislocations can in fact dominate your mechanical behavior because they're so difficult essentially to work with, because they're pinned, they will not move. So they will affect next time the types of plastic deformation we'll expect, or the types of plastic behavior that we'll see.